So far in this DVD we've seen vector addition, vector subtraction, and we've seen vector scalar multiplication. But what about vector-vector multiplication? What about if we want to multiply one vector by another vector? Well, there are actually two different types of vector-vector multiplication. One that's going to result in a scalar value, and one that's going to result in a vector. Now, logically, some people call these the scalar product and the vector product, respectively. But they are more commonly called the dot product and the cross product, due to the symbols that we use when we're writing these two products. Now we're going to take a look at the dot product, which is also known as the scalar product, in this video, which multiplies two vectors together to get a scalar value as a result. And in the next video, we're going to look at the cross product, also known as the vector product, which multiplies two vectors together to get a vector as a result. Now the dot product is one of the most fundamentally important vector operations for computer graphics and programming. As we're going to see during this video, it enables us to find the angle between two vectors. And this is incredibly useful for any area of computer graphics or programming that makes use of vectors. For example, modeling operations, character rigging, lighting calculations within shaders, finding the relative orientation between characters in a video game. All of those examples can utilize and benefit from being able to find the angle between two vectors, and thus they can benefit from the dot product. Now, as we mentioned earlier, the dot product is thus named because of the symbol that we use when we're writing this particular operation. So if I had two vectors, if I had a vector A and a vector B, if I wanted to multiply these two vectors together using the dot product, we would write this as A dot B. Now it is worth noting that in some textbooks the dot product is written as a dot in a small circle, so it's written A dot B like this. This is the exact same thing. This is equivalent to A dot B. They're the exact same thing, they're just a different way of writing it, a different notation based on the preference of the author of that particular textbook. So if we were multiplying these two vectors together using the dot product, we'd write A dot B, and we know from our earlier discussion of the dot product that it's sometimes known by a different name. It's sometimes known as the scalar product because the result of the dot product is a single scalar value. So A dot B is equal to some scalar value S. But what is this scalar value S, and how do we calculate it? Well, actually, the scalar value S is of great significance to us because we define the dot product of A dot B as being equal to the magnitude of A multiplied by the magnitude of B multiplied by the cosine of the angle between those two vectors. So we can see that the length of A, the magnitude of A, that's just a scalar value. The length of B, the magnitude of B, is just a scalar value. The cosine of an angle is a scalar value, therefore we've got a scalar multiplied by a scalar multiplied by a scalar. All three of these, of course, are going to multiply to give us a scalar value. So A dot B is equal to a scalar value, and that scalar value is defined as the length of A times the length of B times the cosine of the angle between. So obviously the dot product is going to be very useful to us, because if we had two vectors, if we had a vector A and a vector B in our 3D space, then we can use it to find the cosine of this angle between the two vectors. Now it is worth noting, and this may get a little advanced for some of you, so if this doesn't make sense now, it should make sense after you've seen the cross product in the next video, but it is worth noting that this angle between the two, this angle of rotation if you will, is the angle of rotation based on, if we had our vector A and our vector B in 3D space, we're going to find an axis that is perpendicular to A, it's at a right angle to A, and it's at a right angle to B, and it's that axis that we're measuring this angle of rotation on. Now again, this will become more apparent how we'd go about finding this axis and why this axis is important to us in the next video where we're dealing with the cross product. You don't really need to worry about it too much here, but if you are going to be applying the dot product to find the angle between two vectors, it is worth noting, well, what axis is that angle actually being rotated around? How would we rotate our vector A, for example, about a particular axis to line it up with vector b? Well, in order to do that, you need to know the axis of rotation, and that axis of rotation, once again, is the only axis that's right angled to A and a right angle to B. Again, how you'd calculate that axis will become apparent in the next video. We don't need to worry ourselves about it here, but I did want to point that out just so that you are aware that that is where we're going to be rotating about. It's the angle of rotation that's about an axis that's perpendicular to both A and B. But we can see that the dot product is going to be incredibly useful to us, because if we know the value of the dot product and we know the lengths of the two vectors involved, we can find the angle between those two vectors. But how can we calculate the dot product of A and B if we don't already know the length of A, the length of B, and the cosine of the angle? Because it's all very well saying, well, we can find the angle between these two vectors if we know the dot product and the lengths. But so far, we've only seen that we can calculate the dot product by knowing the lengths and the angles. So that's not particularly useful to us. So we need some way of calculating the dot product of our vectors when we don't know the length of A, the length of B, or the cosine of the angle between them. Well, for that, we actually need to look at a second definition for the dot product. They're both valid definitions, and they both give us the same scalar value as a result. However, this second definition is defined in terms of the components of A and the components of B, and not in terms of the magnitudes of the vector and the angle between them. So if we had our vectors A and B, if we said that A was equal to the vector x1, y1, z1, and B is the vector x2, y2, z2, then from our earlier discussions on the Cartesian vectors that we saw in an earlier video, we can say that A is equal to x1 times I, our I Cartesian vector, plus y1 times j, our j Cartesian vector, plus z1 times k, our k Cartesian vector. And we've seen why we can write this like this and what these vectors are back in the Cartesian vector video. We can also write B as a combination of those Cartesian vectors. B would be equal to x2 times I plus y2 times j plus z2 times k. So if we were writing our dot product, A dot B, we could write that as x1i plus y1j plus z1k dot, since this is equal to A, so we could write that as A dot x2i plus y2j plus z2k. So we've still got A dot B. But what do we mean by this dot? Well, really, dot is just another way of saying a multiplication. So if that's what we're saying here, a multiplication, well, let's expand this multiplication. And we've seen how we'd expand a multiplication like this. Back in volume 1, we dealt with factorization and expanding of parentheses. So with this kind of multiplication, we need to take x1i and multiply that by the first term of this bracket, plus the second term of this bracket, and the third term of this bracket. We then take the second term of this bracket, multiply it by each of these. We then take the third term of this bracket and multiply it by each of these. It's going to be quite a long equation, but we'd get x1i multiplied by, or dotted with, x2i plus y2j plus z2k. We'd add to that y1j, so this is equal y1j dot x2i plus y2j plus z2k, and we'd add to that z1k dotted with this bracket, so z1k dotted with x2i plus y2j plus z2k. We can then expand this further, as I was saying a second ago, by multiplying each of these out and adding them together. So it's going to become quite a long equation, but if we take it slowly, step by step, it's actually not too hard. So we'd get here x1i dotted with x2i added to x1i dotted with y2j added to x1i dotted with z2k added to y1j dotted with x2i added to y1j dotted with y2j added to y1j dotted with z2k added to, we now need to expand this part of our equation, so added to z1k dotted with x2i plus z1k dotted with y2j, z1k dotted with y2j, added to z1k dotted with z2k. Okay, so what I'd like to do is rearrange this slightly, just one further step. The reason for that's going to become apparent in a second, but what I want to do is I want to collect our scalar values together and our vectors together, because currently what we're saying is we're going to scale a vector and then dot it with the scale of another vector. But we know that we could equally write this as multiplying these two scalars together and then multiplying them by the vectors. If we look at our definition here, if we're saying that a dot b is equal to the length of a times the length of b times the cosine of the angle between them, well then the angle between this vector and this vector is not going to be different to the angle between this vector and this vector, because we're not changing the angles, we're simply changing the scale factors. And if we take that scale factor from here, but instead append it in front, then we're again not changing the value. Now that's maybe going a little bit too into the proof for some of you, so if you didn't follow that, really don't worry about it. All I'm trying to say is that every step we've taken so far is mathematically sound. There is mathematical proof behind why we can expand this like this, but you don't need to worry about that if you don't follow it. And the next step that I'm going to take, which is to collect our scalar values together and then multiply them by the dot product of our two vectors, again is mathematically sound. There is proof behind why we can do this, but you don't need to worry about it in the end. All you need to worry about is the end result we get to. So if all of this expansion doesn't make any sense, it really doesn't matter. But I did want to kind of at least hint at why this works, so those of you who are interested and want to see, well, why can we do this? How can we do this? And how is this mathematically sound? Well, there was a small hint there as to why that is the case without going too involved. So I'm going to rewrite this as x1, x2 multiplied by I dotted with I plus x1, y2 multiplied by I dotted with j. So once again, that's x1, x2 multiplied by I dotted with I, and then x1, y2 multiplied by I dotted with j, then x1, z2 multiplied by I dotted with k. So plus x1, z2 multiplied by I dotted with k. I'm going to add to that y1, x2 multiplied by j dotted with I. So y1, x2 multiplied by j dotted with I, plus y1, y2 multiplied by j dotted with j. So y1, y2 multiplied by j dotted with j, added to y1, z2 multiplied by j dotted with k. So y1, z2 multiplied by j dotted with k, and add that to z1, x2 multiplied by k dotted with I. So z1, x2 multiplied by k dotted with I, added to z1, y2 multiplied by k dotted with j, z1, y2 multiplied by k dotted with j, added to z1, z2 multiplied by k dotted with k, z1, z2, k dotted with k. Fantastic. So this may seem incredibly complicated. It may look like a horribly complex equation, but let's break it down. You'll notice we have a series of scalar multiplications. All of our x components and y components and z components, they are just scalar numbers. So these are just scalar multiplications, which are very easy. We're multiplying one number by another number. We're multiplying two components of the vectors together. We also have a series of vector dot products. And these vector dot products are between our Cartesian vectors I, j, and k. So we need to think back to where we defined our Cartesian vectors, and we know that I, j, and k are three unit vectors where I travels in the direction of our x-axis, j travels in the direction of our y-axis, and k travels in the direction of our z-axis. Now I have noted these are unit vectors here just to sort of enforce the fact that these have a length of 1. But why is that important to us? Why are we interested in the fact that these have a length of 1? Well, remember our earlier dot product equation. Our earlier dot product equation said that a vector A dotted with a vector B is equal to the length of A multiplied by the length of B multiplied by the cosine of the angle between them. Well, in each of these cases, all of the vectors involved in the dot products have a length of 1. They are unit vectors. So whenever we're dealing with unit vectors, and again this only applies because these have a length of 1, we can simplify our dot product equation, because this becomes 1 multiplied by 1 multiplied by the cosine of the angle between them. Therefore, A dot B is equal to the cosine of the angle between those two vectors. Now again, we can only say this when we're taking the dot product of two unit vectors. That is very important. Because we know all of these dot products are between unit vectors, because they're between I, j, and k, we can simplify our equation down to say that that dot product is equal to the cosine of the angle between them. Now, of the different combinations of I, j, and k we have here, we'll notice we have I dotted with I dotted with j, I dotted with k, and all the other various combinations. There are actually two different types of combinations we might have. We either have a combination where we're dotting one of these Cartesian vectors with itself. In that case, we're dotting two vectors that are parallel to each other, and that means the angle between them is equal to 0. So that means the dot product between them, for example, the dot product between I dot I is equal to the cosine of 0, and we know from volume 2 where we looked at trigonometry that the cosine of 0 is equal to a value of 1. So whenever we're dotting two Cartesian vectors together that are the same Cartesian vector, this actually has a value of 1. We've seen that because the lengths are equal to 1, this simplifies down to it equals the cosine of the angle, and because they're the same vector, the angle between them is 0, and the cosine of 0 is equal to 1. So we can go back through, and whenever we're taking the dot product of two Cartesian vectors that are the same vector, this becomes a value of 1. So we had I dot j are different, I dot k is different, j dot I is different, j dot j, they're the same vector, therefore the angle between them 0, therefore the cosine of the angle between them is a value of 1. J dot k is different, k dot I is different, k dot j, they're different, k dot k, these are the same Cartesian vector, therefore the angle between them 0 degrees, therefore the cosine of the angle between them is a value of 1. Fantastic. The other possible combination we might have is where we take one of our Cartesian vectors and we dot it with one of our other vectors. In that case, we know that each of these vectors are at a right angle to each of the other vectors. So whenever we take any of the Cartesian vectors and dot it with any of the other vectors, and it doesn't matter which combination we have, we can take any vector and dot it with any of the others, they're always going to have an angle of 90 degrees between them. So that means if we took our next example, for example, I dot j, so if we took I dot j, that's going to be equal to the cosine of 90 degrees. Well, again, from volume 2, we know the cosine of 90 degrees is 0. So whenever we're finding the dot product of our Cartesian vector with any other Cartesian vector that isn't itself, that value is going to be 0. So I dot j, that's a value of 0. I dot k is a value of 0. J dot I is a value of 0. J dot K is a value of 0. K dot I is a value of 0. And K dot J is a value of 0. Now again, we know this because when we're taking the dot product of any two Cartesian vectors that are different, the angle between them is 90 degrees, therefore the dot product is equal to the cosine of the angle between them, which is equal to the cosine of 90 degrees, which is equal to 0. And again, it's only equal to the cosine of the angle between them because the lengths of both vectors are equal to 1. So our equation that looked pretty complicated before, we've suddenly got rid of all of those dot products, and now we're dealing solely with a nice scalar equation, and a lot of this is going to cancel down because anytime we're taking something and we're multiplying it by 0, we know the result of that is equal to 0. So that means this is going to disappear, this is going to disappear, this right here is going to disappear, this is going to disappear, so's this, and so's this. We also know anytime we take something and we multiply it by a value of 1, that's just equal to whatever we had here. So if we take x1, x2 and multiply it by 1, it's equal to x1, x2. So we can get rid of this part, same here, and same here. So what we're left with is an equation that says the dot product of A dot B is equal to x1, x2, this part, plus y1, y2, plus z1, z2. So again, I will write that somewhere where we have some space. Perhaps I can scroll back up here. Fantastic. It's also equal to x1, x2, plus y1, y2, plus z1, z2. Now this component definition of our dot product is incredibly useful to us because if we know the components of two vectors, then we can use this component definition of the dot product to find the value of A dot B. And if we know the value of A dot B, and we know we can calculate the length of both of the vectors if we know their components, then we know A dot B, we know the length of the vectors, and we can find the angle between those two vectors. Now before we look at doing that, however, you'll notice that from both of our definitions, from the definition that A dot B is equal to the length of A times the length of B times the cosine of the angle between them, and A dot B is equal to x1, x2 plus y1, y2 plus z1, z2, you'll notice that A dot B is commutative. That is to say that A dot B is equal to B dot A. It doesn't matter which order we put our vectors in, we're going to get the same results. And we can see that because we're just taking the x components of each vector, multiplying them together, the y components of each vector, multiplying them together, and the z components of each vector, multiplying them together. And it wouldn't matter which order we had these two numbers in. We know that multiplication of two scalars is commutative. So these would give us the same results no matter which order we put those numbers in. So this is not affected if we switch over our two vectors, we can calculate a dot b or b dot a, we get the same value. And the same is true here. If we're finding the length of a and multiplying that by the length of b, well, if we switched over our two vectors, we've still just got two scalar values that would switch over, and we know scalar multiplication is commutative. The angle between those two vectors isn't going to be changed if we switch over those two vectors, so therefore a dot b is commutative. So that's a lot of theory to take in, but how can we actually use it? Well, using the dot product is very simple indeed. Though the theory may seem quite complicated, actually using the dot product is incredibly simple. So I'm going to bring up a new layer on my whiteboard. And the first thing I want to do is just recap our two dot product definitions. So one is that a dot b is equal to the magnitude of a times the magnitude of b multiplied by the cosine of the angle between them. And the other is that a dot b is equal to x1, x2 plus y1, y2 plus z1, z2. Of course, that's if a is equal to x1, y1, z1, and b is equal to x2, y2, z2. So these are our definitions for our dot product. So let's say that we had two vectors. Let's say I had a vector c that was equal to 2, 4, 0, and a vector d that is equal to 1, minus 3, and 2. And let's say that I wanted to find the angle between these two vectors. Well, the first thing we can do, knowing the components of these vectors, we can calculate the dot product between those two vectors by using the component definition of our dot product. So we know, using that definition, that c dot d is going to be equal to the x-coordinate of c multiplied by the x-coordinate of d. So it's going to be 2 multiplied by 1. So we're going to get 2 multiplied by 1. We're going to add that to the y component of c multiplied by the y component of d. So we're going to get 4 multiplied by minus 3. And then we're going to add to that the z component of c multiplied by the z component of d. So we're going to get 0 multiplied by 2. So if we work that out, we know that 2 times 1 is 2. 4 times minus 3 is minus 12, so we're going to be subtracting 12. And 0 times 2 is 0, so add 0. So we've got 2 minus 12. That gives us a dot product equal to a value of negative 10. So again, we know that this is a scalar value, hence the fact that the dot product is sometimes referred to as the scalar product. It results in a single scalar value. So we know that c dot d is equal to minus 10. But we also, from our other definition of the dot product, know that c dot d is equal to the length of c multiplied by the length of d multiplied by the cosine of the angle between them. So we can rearrange this to find that angle theta. If we divide both sides by the length of c times the length of d, we're going to get that c dotted with d divided by the magnitude of c times the magnitude of d, that is equal to the cosine of the angle between c and d. And then we can apply our inverse cosine trigonometric function to find that angle theta. So theta is equal to the inverse cosine of c dotted with d divided by the magnitude of c multiplied by the magnitude of d. So we can rearrange that dot product definition to find our angle theta. Now we've already said that we know the value of c dot d. We know that c dot d is equal to a negative 10. So we also need to find the magnitude of c and the magnitude of d. So what I'm going to do is I'm going to rewrite our two vectors down where we're working so we can refer back to them without scrolling too much. So c is equal to 2, 4, 0. So c is equal to 2, 4, 0. And d is equal to 1 minus 3, 2. So 1 minus 3, 2. Fantastic. So we can calculate the length of C, the magnitude of C, and these are vectors. There we go. So the magnitude of C, we know, is equal to the square root of x squared plus y squared plus z squared. So it's equal to the square root of 2 squared plus 4 squared plus 0 squared. That's going to be equal to the square root of 4 plus 16 plus 0, which is going to be equal to the square root of 20, which is going to be approximately equal, if I use a calculator for this, approximately equal to 4.4721. So it's approximately equal to 4.4721. We can also work out the magnitude of D. That's equal to, again, the square root of x squared plus y squared plus z squared. So that's equal to the square root of 1 squared plus minus 3 squared plus 2 squared, which is equal to the square root of 1 plus 9 plus 4, which is equal to the square root of 14, which is approximately equal to, if I use a calculator, it's approximately equal to 3.7417 if we were to round that to 4 decimal places. So that's approximately equal to 3.7417. Fantastic. So now we know the length of C, we know the length of D, and we know the dot product of C dot D. So we can say that theta is equal to the inverse cosine of, well, we know that the dot product of C dot D, that was a negative 10. We calculated that using our component definition of the dot product. So that's equal to negative 10 divided by the length of C multiplied by the length of D. So the length of C is 4.4721 multiplied by the length of D is 3.7417. That's divided by that. So it's the inverse cosine of our dot product divided by the length of C times the length of D. So we can now evaluate this. So we know that theta is going to be equal to the inverse cosine of minus 10 divided by, we can use a calculator to work this out, so 4.4721 times 3.7417 is approximately 16.7333 if we were to round that to 4 decimal places. So it's approximately 16.7333, which is equal to the inverse cosine of, if we take minus 10 and divide that by our 16.7333, that's approximately the cosine or the inverse cosine of minus 0.5976, so minus 0.5976. I'm going to keep that value in our calculator because we therefore can find theta is approximately equal to, if I bring the calculator back up, it's going to be the inverse cosine of this. So the inverse cosine is approximately 126.7 degrees. So it's approximately 126.7 degrees. So now that we know our two different definitions for the dot product of two vectors, one using the length of the vectors and the cosine of the angle, the other simply using the components of the vector, we can now use these dot product definitions to find the angle between those two vectors, and hopefully we've seen that actually finding that angle is incredibly simple. Now, before I set some test questions for you to work through on your own, there's actually a little bit more theory I'd like to cover. Now, we briefly touched on this earlier, but I didn't focus on it, and I certainly didn't go into any detail on it. So to put this theory into context, I'd like to examine one example of where we might use the dot product in computer graphics, and that example is in lighting calculations. So I'm going to bring up a new whiteboard so that I can draw a diagram. So if we're rendering a scene, we might often be shading points on polygons. So we may have a polygon in our 3D space, and our camera is looking at this polygon, and we decide that we need to render a particular point on that polygon. We need to evaluate a shader at that point on the polygon. Now for that point on the polygon, we know the surface normal of the polygon, which is a vector. So we know our surface normal, which I can call a vector n. And we also know we're going to have all of the light sources that will be illuminating that particular polygon in our scene. Now for our example, let's just say we have one light source. We have a little point light source off down here to the side. Now if we know the light source and we know our surface, often for the lighting calculations we actually need to know the angle between our light and the surface normal of that surface. In order to do that, we can construct a vector from our point that we're shading out to our light source. So I can call this vector L for the light vector. And if we know two vectors, we know that we can use our dot product calculations to find this angle between the light source vector and the surface normal. So we know that L dot n is equal to the length of L multiplied by the length of n multiplied by the cosine of that angle, which means we can rearrange this to find the angle, because we know that the cosine of the angle is equal to L dot n divided by the length of L times the length of n. Now as an aside, the Lambert lighting model actually uses the cosine of an angle between the light source and the surface normal to calculate the diffuse illumination that reaches the surface at that point. So this equation right here, where we're working out the cosine of the angle between those two vectors, that is actually the basis of the Lambert lighting model, which is used as the basis for diffuse lighting calculations in pretty much every renderer everywhere. So that's actually pretty cool, but I'm getting a little bit out of what I was trying to talk about. But we have this equation, and we're going to be evaluating this equation hundreds of thousands of times, because every point that we're shading, and we know there's going to be many thousands of those points, because every pixel in our image, or even maybe extra samples if we're oversampling for anti-aliasing, etc., every point that we're shading is going to need to evaluate this equation. And it's not going to need to evaluate this equation once, it's going to need to evaluate it for every light source that is illuminating that surface. So that's a huge amount of evaluations. Now finding the length of a vector is actually quite an expensive operation, because it involves a square root. Now square roots aren't exactly slow, but they're nowhere near as quick as a simple scalar multiplication or scalar addition, for example. And when you're executing hundreds of thousands of square root calculations, all of those square root calculations are going to start to have an impact on the speed of our calculations. So notice, however, what would happen to our equation, and we did see this earlier, when both of our vectors have a length of 1. That is to say, both our normal vector and our light vector are unit vectors. We know if they are unit vectors and they have a length of 1, then we know this equation becomes the cosine of theta is equal to our light vector dot our normal vector divided by, well, the length of our light vector is 1 because it is a unit vector rather. The length of our normal is 1 because it's a unit vector. So that's equal to L dot n over 1 times 1 is 1, which is simply equal to L dot n. So notice, if it's simply equal to L dot n, we can use the component definition of our dot product in order to find the cosine of that angle. So if we said that L was equal to the vector Lx, Ly, Lz, and n was equal to the vector nx, ny, and nz, then we know that we can find the cosine of the angle using that component definition, using Lx times nx plus Ly times ny plus Lz times nz. This is simply using scalar multiplications and scalar additions. So it's a lot more efficient than this version of our calculation would be, where we need to use a square root. So in many scenarios, we can actually normalize a vector once and then use that normalized vector time and time again within our vector operations, such as the dot product operation. And that's going to result in much faster calculations and thus a more efficient program. So in our rendering example here, if we have all of our polygonal surfaces in our 3D scene, we could store the surface normal as a unit vector. And that means that we'd only ever need to calculate the length of our vector once. We'd need to calculate it when we first create that surface. We'd calculate our normal vector. We'd then have to find the length of that vector in order to normalize it so it becomes a unit vector. We've evaluated that square root once. We can then store that unit normal vector and use that for every single time we're evaluating those lighting calculations, and that's hundreds of thousands of times per frame. So it's going to have a huge impact on the efficiency of our rendering. Now granted, because this lighting vector is different for each point that we're rendering and for each light that we're rendering, we would need to calculate that vector and then normalize it for each point we're rendering, each light we're rendering. So we'd still have a number of square roots because of that, but we'd only have the one square root rather than two square roots for both vectors. And actually, when you get into more complicated lighting models where we may use in a single shader evaluating for a single light on a single point, you may actually need to use multiple different dot product operations on various vectors. Therefore, even if our surface normal, say, was normalized and we calculate this light vector and that's not normalized, it may be more efficient to normalize that vector once at the start of the shader that's going to be evaluating these lighting calculations, and then use that normalized vector in all of the other dot product operations, cross product operations and the likes that we have after that point. Because by using normalized vectors, by using unit vectors, it can save a lot of overhead in terms of our rendering efficiency for this example, in terms of all the calculations that are involving the dot product of vectors. And since the dot product is such a fundamental operation, it's used so frequently in computer graphics, it is worth noting that if we are using unit vectors, if we're using normalized vectors, we can make our calculations a lot more efficient, and that means our programs are going to run faster. So that is really, really important. Alright, so now that we've seen all of that theory behind the dot product, also known as the scalar product, it's now your turn to apply this theory to answer some questions. So I'm going to bring up a new layer on our whiteboard. Fantastic. And question 1, I'm going to give you two vectors. I'm going to say we have a vector A, which is equal to 3 in x, 2 in y, and 1 in z. And we have a vector B, which is equal to 2 in x, 5 in y, and 4 in z. And for question 1, I'd like you to calculate the dot product of these two vectors. So I'd like you to find that single scalar value that is the dot product of these two vectors. So if you go ahead and pause the video, attempt to find the answer on your own, and once you have a solution, or if you get stuck, you can unpause the video and I will work through the answer here on the whiteboard. Okay, welcome back everyone. So we're searching for the dot product of these two vectors, and since we know the components of our vectors, it's going to make sense to use the component definition of our dot product. So we know the component definition of our dot product is that A dot B is equal to x1, x2, plus y1, y2, plus z1, z2, which means A dot B is equal to x1, 3, times x2, which is 2, plus y1, which is 2, times y2, which is 5, plus z1, which is 1, times z2, which is 4. So this is going to be equal to 3 times 2 is 6, plus 2 times 5 is 10, plus 1 times 4 is 4, which is equal to 6 plus 10, 16, plus 4 is 20. So the answer I was looking for is that the dot product of A, dot b is equal to 20. Now if you got stuck at any point, just make sure you're familiar with the component version of our dot product definition. The fact that the dot product of these two vectors is equal to the x components multiplied together plus the y components multiplied together plus the z components multiplied together. And if you're familiar with that, then just make sure you haven't made any simple numerical errors with the actual calculations. So that's question 1. Moving on. Question 2 is going to be a similar question. Again, I'm going to give you two vectors. In this case, this is vector c, which is equal to, let's say, 9 in x, minus 2 in y, and 3 in z. And a vector d, which is equal to, I don't know, let's say minus 3 in x, 0 in y, and 1 in z. And again, I'd like you to calculate the dot product of c dot d. So go ahead and pause the video, and when you come back, I'm going to work through the solution here on the whiteboard. Okay, welcome back everyone. So we're searching for that dot product. Again, we're going to use our component definition of the dot product, which means I'm going to take the x and multiply that with the x of our second vector, so that's 9 multiplied by 3. I'm going to add that to the y's multiplied together, so that's minus 2 times 0, and add that to the z components multiplied together, so that's 3 multiplied by 1. So 9 times 3 is going to be 27. Of course, this is a negative 3, so I must make sure that negative doesn't get dropped. So 9 times minus 3 is minus 27, plus minus 2 times 0 is 0, plus 3 times 1 is 3. So we've got minus 27 plus 0, still minus 27. Then plus 3 is going to give us minus 24. So the value of c dot d is equal to minus 24. That's the answer I was looking for that question. Alright, so moving on once again, we're going to tackle another question. And I think I'm going to use a new whiteboard just in case I need extra space for working out in a second. So this is question 3. Again, I'm going to give you two vectors. Vector e is equal to 4 in x, 3 in y, and 6 in z. And vector f is equal to 2 in x, 1 in y, and 3 in z. And what I'd like you to do, if I tell you that e dot f is equal to the length of e multiplied by the length of f multiplied by the cosine of the angle between them, we know that this is the definition, one of our two definitions of the dot product. What I'd like you to do is rearrange this to find the angle that is between these two vectors, and then use that to find the angle between those two vectors, please. Okay, welcome back everyone. So we've already seen how to rearrange this equation, and it should be very simple, but just to work through that here, we know if we divide both sides by the length of e and the length of f, they're going to come down underneath our e dot f and leave the cosine of the angle on its own. So we're going to get e dot f divided by the length of e times the length of f is equal to the cosine of our angle, which means that theta is equal to the inverse cosine of e dot f divided by the length of e times the length of f. So now that we've rearranged that, I ask you to find this angle theta. So to do that, we're going to need to calculate e dot f, we're going to need to calculate the length of e, and we're going to need to calculate the length of f. So let's start by calculating e dot f. So e dot f. And we can do this using our component form of the dot product definition. So we've got e is equal to 436. So e is equal to 436. And f was equal to 213. Since we're going to need to refer to this quite a bit, I'll write that down here. Fantastic. So e is equal to 436, f is equal to 213. So the dot product is going to be equal to x times x. So 4 times 2 plus y times y, 3 times 1 plus z times z, 6 times 3, which is equal to 8 plus 3 plus 18, which is equal to 8 plus 3 is 11 plus 18 is 29. We also need the length of both of our vectors. So the length of E, the magnitude of E, is equal to the square root of 4 squared plus 3 squared plus 6 squared. It's the square root of x squared plus y squared plus z squared. So 4 squared plus 3 squared plus 6 squared, which is equal to the square root of 16 plus 9 plus 36, which is equal to the square root of 25 plus 36, which is the square root of 61, which is approximately equal to, if we bring a calculator up, the square root of 61 is approximately equal to 7.8102. So that's approximately equal to 7.8102. We now need to find the length of f. So the length of f, the magnitude of f, is equal to the square root of x squared plus y squared plus z squared. So that's 2 squared plus 1 squared plus 3 squared. So 2 squared plus 1 squared plus 3 squared. That's going to be equal to the square root of 4 plus 1 plus 9, which is equal to the square root of 14. And that is approximately equal to, if we use our calculator, approximately equal to 3.7417 if we were to round this to 4 decimal places, to 3.7417. Fantastic. So we now know E dot f, we know the length of E, and we know the length of f. So we can rewrite this equation because we know theta is equal to the inverse cosine of E dot f, which we calculated as 29, divided by the length of E, 7.8102, multiplied by the length of f, 3.7417. So we can use a calculator to help us solve this. So that's equal to the inverse cosine of 29 divided by, let's bring our calculator up, so 7.8102 multiplied by 3.7417 is approximately 29.2234. So 29.2234. So we're taking 29 and we're dividing that by 29.2234, which is equal to 0.9923 and then a load of numbers. And we want to take the inverse cosine of that. So inverse cosine, we are in degrees, so our value is 7.089 degrees. We could say 7.1 degrees. So our angle theta is approximately equal to 7.1 degrees. So the angle you were after, the angle between those two vectors, is that angle right there, 7.1 degrees, or an angle that's close to that based on how you rounded your numbers as you were working through the answer. So again, if you did get stuck at any point, the first thing to note is that we needed to be able to rearrange this equation. Now we did see that earlier in the video. It's quite a simple equation to rearrange. We just take the length of E and the length of F, we divide both sides by that, and that gives us this equation. And then of course to find theta we need to use the inverse cosine, which gives us this equation here. If you got stuck with that at any point, do refer back to the earlier part of this video where we rearranged it, and if that still doesn't make sense, then refer back to our earlier volumes on both rearranging equations in volume 1 and the trigonometry involved here with our inverse trigonometric functions that we saw in volume 2. As long as you got this equation rearranged successfully, the only other tricky bit was remembering we need to use the component definition of our dot product to calculate E dot F. If you did that, just make sure you did get the same value here, 29. There weren't any small numerical errors, because they do crop up, they always crop up, and they affect everyone, myself included. So just double check your workings, make sure there aren't any errors there. And then make sure you calculated the length of E and F correctly by taking the square root of x squared plus y squared plus z squared. If you did that and then put them back into our equation for theta, you should have got an angle that's approximately equal to 7.1 degrees. There's just one last question that I'd like to set in this video, so I'm going to bring up a new whiteboard for that. Okay, so question 4. Now this is going to be quite a tricky question. It's going to get you thinking, but you do know everything that you need in order to solve this. But it will get you thinking, it will need you to problem solve, because I'm not just going to hand you the problem on a plate, so to speak. I am going to require that you think about the problem a little bit. So the problem that I have is I have a polygon in a 3D scene, and I know that this polygon has a surface normal, which I'm going to call n, and this normal is the vector 3, 5, 1. So I have a polygon in a scene that has that surface normal, and I have a camera at the origin of my scene. So this is my origin of my scene down here, and I have a camera right down here at the origin, so it's at 0, 0, 0, and that camera is seeing a point on this surface. So we have a point on the surface, and this point I'm going to call, let's call this point P, has the coordinates 1, 2, minus 3. So I've got a camera, and it is looking at that point P on the surface. So it's sitting at the origin, our camera, it's looking directly at this point P, which has the coordinates 1, 2, minus 3. And this point exists on a flat polygon where all of the polygon uses this surface normal n that is 3, 5, 1. So that's the scene that we have. The question that I'd like you to answer is this camera looking at the front face of our polygon or the back face of our polygon? Now what I mean by that, if I was looking directly down the side of my polygon, so I've got a triangle, but I'm looking directly at the side of the triangle, we know that this triangle is going to have a surface normal that sticks out from the triangle. If we're looking at this side of our triangle, we're looking at the front face. That's the side where the surface normal sticks out from. However, if our camera is behind this triangle and looking at the other side, we're looking at the back face. Now, short of looking directly down the side of our triangle, we're either going to be looking at the front face or at the back face of our triangle. So what I'd like you to answer is, given that we know our camera's sat here at the origin and it's looking at this point, it's looking at the point 1, 2, minus 3, and that point is sharing that surface normal 3, 5, 1, are we looking at the front face or the back face of the polygon? Now again, this is quite a tricky question, but take your time, think about it, and you're going to realize that actually we know everything that we need in order to solve this problem. So go ahead and give this an attempt, and once you have a solution, or if you get stuck, unpause the video and I will work through the entire solution here on the whiteboard. Okay, welcome back everyone. So I hope you had fun with that, and I hope that you've got a solution. So we're going to work through the answer here on the whiteboard, and once you start to think about it, it's actually not as hard as it first seems. So the first thing that I need to do is I want to construct a vector that goes between our camera and the point on our surface. Now it doesn't matter if the vector points from our camera to that point, or if it points from the point to the camera, as long as you're aware of which way you've constructed this for the later calculations. Now the way I'm going to construct it is so we have a vector that points from this point down at our camera, and I'm going to call this vector C. It's our camera vector. So I'm going to create this vector, and we've already seen in earlier videos how we can create a vector between 2 points. Our vector C is going to be equal to the position vector of our end point, which I'm going to call end, minus the position vector for our start point. So I'm ending here at the origin, and I'm starting here at the point 1, 2, minus 3. So it's equal to our origin minus that point on the surface, 1, 2, minus 3, which means our camera vector C is equal to the vector 0 minus 1 is minus 1, 0 minus 2 is minus 2, 0 minus minus 3 is positive 3. So it's equal to minus 1, minus 2, 3. So we've got that camera vector. This is a vector that's telling us effectively the direction our camera is looking in, but I've chosen to have a vector that points in the opposite direction. And we also know we have the surface normal on our surface, but this normal is going to be the same normal for any point on our surface, which means we can think of this normal being the same normal as exactly the point we are looking at. And we know that our vector is free to float around Cartesian space, so it could quite happily be sat there where that point is. And what I'm interested in finding is the angle between our normal and that camera vector. If we look at this, if I've got a camera sat here that's looking at a surface, and I've got my triangle, now what I'm going to do is I'm going to draw the triangle as if we're looking down the side of it. So again, and I erased my diagram from earlier, if I had a triangle, I'm looking directly down the side of the triangle now. So what I've got is I've got a surface normal that's pointing out to one side, and I've got a normal that's pointing at our camera. Now hopefully we can see, because I've created this normal so it points from our surface to the camera, if our normal and our camera vector here, if they have an angle between them of 0 degrees through to 90 degrees, we know that our surface is going to be facing our camera. We're looking at the front face of our surface, and we can see this if I was to start rotating the surface around. So if I started rotating the surface around, our surface normal would stick out like this, and we can see here's our angle, and we can keep increasing this angle and keep rotating our surface around up until the point where that angle equals 90 degrees. When it equals 90 degrees, we're staring right down the side of our triangle. So all the time it's between 0 degrees and 90 degrees, then we're looking at the front face. However, once we pass 90 degrees, so once we continue rotating and we go past 90 degrees, so we're now greater than 90 degrees here, so greater than 90 degrees, our camera is now looking at that back face of the polygon, because here's our front face, and we're not looking at that, we're looking at the back face of our polygon. So from 90 degrees all the way up to 180 degrees, where we're staring right at the back of our polygon, we're staring at the back face of the polygon. So from 90 degrees to 180 degrees, we're looking at the back face. Now it's worth noting that if you constructed your vector the other way, so instead of a vector from the surface to the camera, I'll draw our camera lower down so we have some more room. If you constructed this the other way, so you had your camera, you had your surface, and you created a vector from the camera to the surface, notice the angle between these vectors. We've got a vector like this and a vector that's pointing in this direction. The angle is actually going to be greater than 90 degrees all the time we're looking at the front face, because if we were to draw the same process we had before, so we went from 0 to 90, so we have our angle, our surface normal pointing directly at the camera. Our camera vector is going to be pointing in the opposite direction. The angle between those two vectors is 180 degrees. As we start rotating away from the camera, that angle is going to get smaller and smaller, because we have to think of it as, because our vector's pointing in this direction, when we bring them beginning to beginning, our camera vector is actually pointing over here. As we rotate our surface away from the camera, this angle is going to get smaller and smaller and smaller, up until the point where, again, that angle is 90 degrees because our surface is 90 degrees to the camera. So our camera vector would stick out over here and we get 90 degrees. We're looking directly down the side. So if you were to have represented that vector rather than going from the point to the camera, if you went in the opposite direction, the angle that you get between your normal and that vector is going to be different, and the relationship between the front face and the back face is going to be different, because it's going to be from 180 degrees to 90 degrees that you're looking at the front face, and from 90 degrees to 0 degrees that you're looking at the back face. So again, it doesn't matter which way you construct that vector as long as you take note of it in your later calculations. So if, like me, you've constructed a vector that goes from the point on the surface to the camera, then you're looking for an angle that, if it's between 0 and 90 degrees, we're looking at the front face. And if it's between 90 and 180, we're looking at the back face. However, if you've constructed the opposite vector, when you work out the angle between those vectors, you're going to get a different angle to me. And you're going to be looking for an angle between 90 degrees and 180 degrees if it's a front face, and 0 degrees and 90 degrees if it's a back face. So that is important to note. It doesn't matter which approach you take. Much like many problems that you solve, there can be multiple approaches. What matters is you're very careful when you're thinking about the problem to know how have you set the problem up, how are you approaching solving that problem, and make sure you think about the maths involved so that you know what answers you should be expecting. So here, because of the way I've constructed that vector, I know that an angle between 0 and 90 is a front-facing angle, and an angle between 90 and 180 is a back-facing angle. So I'm going to clear some room now for our calculations. So I hope all of that made sense, because I'm hoping that most of you are coming from a graphics background and understand an idea of a camera in a scene and rendering a point on a surface. Even if we're not really worrying about any of the true calculations, I'd hope that you're comfortable with the idea of a triangle, a surface normal, how that defines the surface normal of that triangle, how it defines the orientation, rather, of that triangle, and a camera and how that can have a vector where it's looking down. If you don't, then maybe this problem will have been a little bit beyond the scope of what you would have been able to tackle, and that's okay. Maybe you can sit and watch this, see where I'm going with it, follow as much as you can, and don't worry if you don't understand it, because if you're not dealing with cameras and surfaces and things, then you probably aren't going to be applying the vector mathematics we're looking at in these DVD to those kind of problems, so it doesn't really concern you. So we've got our vector, and we've got our vector c, and we've also got our normal vector n, and we said our normal vector is 3, 5, 1. So we've got c, and we've got n is equal to 3, 5, 1. And what I want to do is find the angle between these two vectors, and we've seen how to do that using our dot product. So I know that the angle between these two vectors is going to be equal to the inverse cosine. So I don't quite know why I was writing a hat there. The inverse cosine of, and I've named these vectors c and n, so it's going to be the inverse cosine of n dot c divided by the length of n times the length of c. So in order to calculate that, I need to calculate n dot c using our component definition of the dot product, and I need to calculate the length of both vectors. So let's start with n dot c, and that's going to be equal to, so n is 3, 5, 1, c is minus 1, minus 2, 3. So I'm going to write these again. So n is equal to 3, 5, 1, and c is equal to minus 1, minus 2, 3. So n dot c is going to be 3 times minus 1 plus 5 times minus 2 plus 1 times 3, which is equal to minus 3. 5 times minus 2 is minus 10, and 1 times 3 is plus 3. So the minus 3 and plus 3 are going to cancel, and that's going to give us the n dot c is equal to minus 10. Fantastic. We also need to work out the length of n and the length of c. So the length of m is equal to the square root of x squared plus y squared plus z squared, which is equal to the square root of 9 plus 25 plus 1, which is equal to the square root of 35, which is approximately equal, if we use a calculator, to 5.9161 if we were to round that to 4 decimal places. So 5.9161, fantastic. The length of c is equal to the square root of x squared plus y squared plus z squared, so minus 1 squared plus minus 2 squared plus 3 squared, which is equal to the square root of 1 plus 4 plus 9, which is equal to the square root of 14, which is approximately equal to, if I bring a calculator up, that's approximately equal to 3.7417 if I round that to 4 decimal places. So 3.7417. So we now know the value for n dot c, the magnitude of n, and the magnitude of c. So we can work out this value right here, take the inverse cosine of it, and that will give us our angle. And we can then compare that angle to see, are we a front face or are we a back face? So we need to find theta, which is equal to the inverse cosine of n dot c, which was negative 10, divided by 5.9161, the length of n, times 3.7417, the length of c. Fantastic. Which is equal to the inverse cosine of minus 10 over, so 5.9161 times 3.7417. So that's 22.1363. So 22.1363, which we can then work that out. So we're going to take minus 10, we're going to divide that by 22.1363. That is equal to a negative 0.4517, and so on. We're going to take the inverse cosine. So inverse cosine, and we can see that our angle is approximately 117 degrees. So theta is approximately 117 degrees. So what is this telling us? It's telling us this angle right here between our surface normal and our vector pointing to our camera is 117 degrees. Or what did we say earlier? Up to 90 degrees we're facing the camera. We can see that all the time we're facing towards the camera. Up to 90 degrees our triangle is facing the camera. But we've gone past 90 degrees. We're now at 117 degrees. And to get 117 degrees, our triangle must now be facing away from the camera. We're looking at the back of the triangle. So in answer to the overall question, given this particular triangle, given the normal of the triangle, the position of the camera, and the point we were rendering, we are rendering the back of the triangle. We're looking at the back face of that triangle. Now, techniques like this can actually be used in a 3D application to apply what's known as backface culling. And in backface culling, we test each polygon that we're looking at with a camera, and we only draw the polygons that are front facing to the camera. So we only draw the polygons where we're looking at the front face. And that's a technique that can be used to speed up the rendering of a viewport in a 3D application, because we assume if we're looking at the back face of a polygon in a solid object, we shouldn't really be able to see any back-facing polygons, because they should be hidden by polygons on the other side of the object that are facing us. Now that's getting a little bit out of the scope of vectors. Obviously that's dealing with modeling and those kind of operations, but I wanted to note that in a 3D application, the technique we've just used in this question can actually be used to apply what's known as backface culling. So I think that's pretty cool. So to recap everything that we've seen in this video, and to do that I'm going to bring up one last layer for this video. We know that the dot product of two vectors can be defined in two different ways. We have A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between A and B, and we have that A dot B is equal to x1, x2 plus y1, y2 plus z1, z2. Of course, that's if A is equal to x1, y1, z1, and B is equal to x2, y2, and z2. We know this is also called the scalar product because of the fact that it gives us a single scalar value as a result. We've seen how we can rearrange our first definition in order to find the angle between the two vectors. We can rearrange that so that theta is equal to the inverse cosine of A dot B divided by the magnitude of A times the magnitude of B. So we have seen how we can rearrange our first definition to find the angle between the two vectors, and we've discussed how we can make the calculations more efficient if those two vectors are both unit vectors, because the magnitude of those vectors is 1. Therefore, this equation right here simplifies down, and we get that if they're unit vectors, the angle is equal to the cosine, or the inverse cosine rather, of simply A dot B. We can calculate that using our second definition, the component definition, and that's actually quite an efficient calculation. So I really hope that this video has helped to demonstrate how incredibly powerful vectors can be when we're working in computer graphics and programming, along with introducing one of the most important vector operations you will ever encounter, the dot product, which is also known as the scale product, or the scalar product rather. So I really hope you've enjoyed this video. I really hope that it's sort of given you an understanding of the true power of vectors in both computer graphics and programming, and the true power of our dot product or scalar product. So thank you so much for watching, and I'll see you in the next video.